really just captures the imagination. It fascinates us, but it also captures the imagination of the public because it actually does make the front cover of popular magazines like Newsweek. Even though it does capture the imagination of the public, you also know, and we all know that journalists often get it wrong. And just as a side note, even though this is here on the cover of Newsweek, there are two mistakes on the cover. The first one is it says this is the picture of CMS, and it says that CMS is the biggest experiment. Actually, it's not the biggest. Atlas is the biggest. It's the heavier one of the two, but Atlas is the bigger one. And the other one, which is I think a big mistake, it says it's European, and it's not European because the US has contributed more than 30% to both of these experiments and has contributed significantly in actually the machine. But with these experiments, we tried to get at the science, and for the last couple of years, the field has also made, I think, enormous strides in getting at the science. 2 years ago, both the Atlas and CMS experiments discovered the Higgs boson, and this is a picture of the Higgs decaying into 2 gammas. Then, the experiment at DIA in China has a reactor neutrino experiment, has measured one of the last remaining parameters in the PMNS matrix for the neutrino oscillations, and measured the angle sine squared theta 1,3, and measured it to be rather small. And then, as you all read, I'm sure, it's that 2 weeks ago, the BICEP collaboration had the first evidence of actually inflation and gravitational waves by looking at the cosmic microwave background radiation. And they measured this parameter R. So here is the power spectrum as function of angular momentum. And this split here is the indication that R, which is the ratio of the tensor to scalar ratio, so really, the effect of gravitational waves is actually much larger than people had expected. So the question then is, or to just put this in perspective, particle physics, of course, has not done this alone. It has relied tremendously on other science disciplines. But at the same time, particle physics has had a broad impact for other sciences and for society as a whole. So the question is, what are the key connections and the synergies between these tools, techniques, and technologies developed for particle physics and other disciplines? So what I would like to do is to look at these impacts, and go over them one by one. So what I would like to do is first look at the detector technology, then go into computing, accelerators, and then facilities. And then I will conclude with what I view as some outstanding issues, and then especially what the opportunities are for all of us. So first, detector technologies. So this is a major area of connection of particle physics that has reached, I think, all the way from medical industry to actually imaging detectors. So one technology that I would like to highlight is the silicon technology. The silicon technology that high-energy physics started and brought it to such an unprecedented scale that we see now realized in these LHC experiments actually had its beginnings in industry. It is because industry developed, the lithography and the integrated circuits. Is that what, particle physics capitalized on and started to make these silicon detectors. So again, it had very humble beginnings. Here's a picture of 1987 of an experiment at Fermilab where the area of silicon here is about 25 square centimeters. That developed all the way to, current experiments where the area of silicon is more than 200 square meters. In parallel with that, what was developed is application-specific integrated circuits. So these are integrated circuits that read out these devices. Now, believe it or not, that this technology that lies at the basis of this has been applied in neurobiology. Because, so it was, in some sense, the crossing of the path of a particle physicist and a biologist to try to understand that the problem that the biologist faced is he said, he wanted to measure the nerve pulses at the end of a retina. And what they developed is exactly the same methodology that we use in silicon detectors because you have, a battery of electrodes, you wire bond it, and you read it out with an application-specific integrated circuit. So you use exactly the same methodologies and the same techniques and the same readout circuitry that was developed for particle physics to study the eye. And what they discovered actually that there's a new functional time of the retinal output that was not known before they did this. The other area where particle physics has had a tremendous influence, and still has a tremendous impact, is medical imaging. So here in proton-computed tomography, what you do is, it's much better than tomography with gamma scattering. It's where you use photons. So you measure the direction of photons very precisely before the object, very precisely after the object. So you measure the scattering, and you measure the energy loss of the proton in a calorimeter behind it. So this proton-computed tomography is being developed at the University of Santa Cruz, and what they use is, again, silicon detectors, silicon strip detectors, to measure the trajectory of particles, and then a calorimeter to measure the energy loss. And the readout of this is exactly the same readout that was used for the glass Fermi telescope that is up in space. The main difference between this application and the application in space is that if you want to do proton-computed tomography, you have to read these out. You want to measure, 1 million protons per second to actually be able to image, a person very rapidly. Now, this technology, has migrated to nuclear physics. Even here at JLab, there is the JLab Class 12 experiment where part of the ASICs that were developed that are being used to read this out were developed at Fermilab, and also at Phoenix. The SVT at Phoenix uses the readout that was developed at Fermilab for run 2, and some of the assemblies actually occurred also at Fermilab. Now, one way to go beyond where we currently are, to increase the power of where we currently are, is to go in a different direction with silicon technology, and that is using what they call monolithic active pixel sensors. So in a monolithic active pixel sensor, what you do is you have a sensing medium, which is still silicon, but in the sensing medium, right on top, you also have the first stage of your front-end electronics. So you can do the processing, and you can put the logic and the intelligence right there where you do the measurement. Now, this technology was conceived by the particle physics community, but at the moment, it's the nuclear physics community, it's you guys, who are really running with it. So the first application of this technology is in the STAR heavy flavor tracker, where they have a couple of layers of silicon detectors. And the further development of this technology would, again, really be very beneficial to particle physics. Again, to indicate you that the nuclear physics community is really pushing this technology very, very hard, is here is a picture of the ALICE inner tracker system, which is looking at the construction of a 7-layer tracker that will use 25 gigapixels. It's the largest pixel detector that has ever been built. Similarly, for the experiment at GSI, where again the first 4 layers are going to be built with this technology, with the added requirement that it also has to be radiation hard, which is really something that the particle physics community will be very interested in. Now, the pixel technology, the silicon pixel technology, has also spun off into the X-ray community. So while the CMS pixel detector was being developed, and here's a picture of the CMS pixel detector, they realized actually that you could use the same technology to also measure X-rays. And a company was spun off called Dectris that has developed, these X-ray detectors, which are now the workhorses at almost any light source. Now, taking this even one step further, in Europe at the XFEL, there are a couple of X-ray detector projects that are being developed. The 3 are shown here. One is a hybrid pixel detector, the other one is a large pixel array, and the other one uses another technology that came out of the particle physics community. But again, these are all built as a collaboration between the particle physics community and the high energy physics community to enable their science. Now, integral to all of this technology is the readout. So as I mentioned already, application-specific integrated circuits were fully pushed by the particle physics community, and this is, I think, a rather interesting example of the path that these technologies have followed. So in around 1999, the nuclear physics community actually needed a readout for the ALICE experiment at the LHC, and they developed a chip that was used for the pixel detector at ALICE. Then the project essentially stopped because there were no follow-on projects. But while working on the project for ALICE, they realized that this was a damn good chip to also use for X-rays. So out of this came the development of the Medipix and the TimePix development that is now being used to make these X-ray images. Now, it turns out that in these 10 years of development, and they really have pushed this development, now they have a chip, the TimePix 3, which almost meets all specifications for the upgrade of the LHCb detector. So it is not, it was, the way I view this is, enlightened management that let this project go on and maybe had a little detour from its path has fully paid back, the investment that was made. And to show you here a picture, this is a picture that was taken by the Medipix 3 chip, which shows the contrast that you achieve with this device. And these are 4 keV, gammas. And the only way you can get this, if you really have single photon efficiency and very, very low noise readout. If you compare this to the X-ray you get from your dentist, the difference is striking. I find it striking. Let me just change track here a little bit, and that is crystal development. So, we knew that AGO, which is this crystal, bismuth germanium oxide, existed in the 70s. But the ALK-3 experiment at lab at CERN decided to actually at one point build an electromagnetic calorimeter using these crystals because it had the best energy resolution. And this is again something that is unique to particle physics, and that is the scale of these devices. So ALK-3 needed about 11,000 of these crystals, and at the time that they wanted it, they could only grow a crystal one at a time. But they contacted this Shanghai Institute of Ceramics, and they developed in conjunction with this company a method where they could build 36 crystals in one shot. And that simply was the breakthrough to make this technology available to the medical imaging industry, because then it suddenly became cost effective. So this opened the medical market, and 1,500 PET scanners have been built by GE Healthcare, using crystals grown by this method by the Shanghai Institute of Technology. Now another example is the development of isocrystals. So during the last phase of the LHC, when CMS was building its electromagnetic calorimeter, they decided to use lead tungstate. One requirement for the LHC experiment is always that everything has to be radiation hard. So when they were looking at the radiation hardness of lead tungstate, what they discovered is a way to make lead tungstate radiation hard. That is through special annealing and yttrium doping. Now at that time, LSO was already discovered by Schlumberger, but somebody put these two together. So somebody, and he gives the particle physics community full credit for that. He says, that because of the yttrium doping, he, invented LISO. LISO stands for lutetium yttrium silicon oxide. So that is the crystal that is now being used most within PET scanners in the medical industry. So here again, and now, in turn, the particle physics community can use these crystals for their next generation of experiments, because the MUV experiment at Fermilab would like to use LISO crystals for their calorimeter. Now, this one I put in because it is the basis of the result from 2 weeks to look at.